Hello, welcome back, students. Today we're going to be doing long and synthetic division, rational functions, and asymptotes. Alright, so last time we left off on talking about the synthetic and long division, but now let's actually try to take a look at the algorithm which will perform our long division. So let's say we're going to immediately start with an example 1. So we have polynomials, right? So we have 6x cubed minus 19x squared plus 16x minus 4. And our goal is to be able to divide it by x minus 2. Okay? And okay, so the way we're going to do that, let's start with the long division of the polynomial. So long division. Very effective algorithm. So essentially, we're starting with writing down 6x cubed minus 19x squared plus 16x minus 4. Then we are drawing this line, and we're going to put x minus 2. Okay, so that means that 6x cubed minus 19x squared plus 16x minus 4 is divided by x minus 2. Now, essentially the way we do it is we're taking the first term and we divide it by the first term here. So we're going to have 6x cubed over x is equal to 6x squared. Right, so let's go ahead and put that here. So we're going to have 6x squared, right, and x to the square. Then we're going to go ahead and multiply. So we're going to multiply 6x squared here and 6x squared times 2. So we're going to have 6x squared times x, that's 6x cubed. 6x squared times negative 2 is going to be negative 12x squared, right? Now we always put parentheses around it, and we put a negative sign in front. So we're subtracting 6x cubed minus this expression, so we're subtracting it by powers. So 6x cubed minus 6x cubed, that is 0. Meanwhile, we have negative 19x squared minus negative 12x squared, so that's plus 12x squared, so we're going to have minus 7x squared. Okay, now we're done with this, right, this line. Now we're moving on to the other line. So what are we going to have here? We have negative 7x squared. So we're going to take this and divide it again by the first term. So we're going to have negative 7x squared divided by x, which is equal to negative 7x. So we're going to put it here, minus 7x. And we perform the same thing. We multiply, right? We multiply by, first we multiply negative 7x by x. And then we multiply it by negative 2. So we're going to have negative 7x times x, that's negative 7x squared. And then negative 7x times negative 2 is positive 14x. Now we put a parenthesis around it, and then, okay, well, we notice that we're missing, here we have x squared, but now we got to take this one down here, so I'm just going to copy it, right? So now we're subtracting, and what are we going to have? Negative 7x squared minus 7x squared, that is, so subtracting it is going to be, so plus here, it's going to be 0, and then 16x minus 14x, that's going to become 2x. Okay, and now the last step, okay, so we have 2x. We're going to go ahead, 2x, and we're going to divide it by the first term. So 2x over x is equal to 2. So we're going to have plus 2. Okay, then we're going to go ahead and take down that negative 4 right over here. And so now we're going to use that 2. So 2 times x, so that's going to be 2x. 2 times negative 2, that's negative 4. Okay, putting parentheses around and subtracting, we have 2x minus 2x, that is 0. Negative 4 minus negative 4, so negative 4 plus 4, that is 0. So our remainder here is 0. So we perfectly divided the equation. So that means our polynomial here is actually equal to 6x squared minus 7x plus 2. Right, so the key thing here, we were trying to figure out if x minus 2 is indeed a factor. Right, and it is actually a factor in this polynomial. So it's very, very helpful for us to know how to do long division, because we are able to find factors and possibly roots of a very difficult polynomials. And let me actually show you an interesting. So I have a very neat from the book. The book provides a very, very neat layout of how you can think about the long division if you got confused during my explanation here. So there is a similar view right here. Okay, so let me go down here. So what we can have here is Again, that's how we proceed, right? How we think. So each step is tell us how to think. I have it in colors here of how we can perform a long division. So now, of course, we can also do that for the quadratic polynomials, but most of the time, quadratic polynomials, it's much easier for us because we can factor out. But let's take a look at an example where sometimes we cannot factor out, but we can still able to divide, right? And let's go ahead and take a look at example 2. So example 2, we're going to have x squared plus 3x plus 5 divided by x plus 2. Okay, so let's write it down as a long division. So we're going to have x plus 2, then x squared plus 3x plus 5. Okay, and once again, we're going to divide our first step, divide this x squared by x. So we're going to get x, right? So we multiply. So we have x times f, that's x squared, x times 2x, that's plus 2x. Then we're going to put parentheses and subtract. So we have a 0. And we have 3x minus 2x, that's just x. We're taking down the 5. So we have that x over x divided by x. That's 2x, so x, let's see, so we have x plus 2. Oh, actually, do we want to do that? Divided by x plus 2? Sure, let's divide it by x plus 2. So we have x over x, so this is going to be x plus 1, right? Because x over x is this. So then 1 times x, that's minus x. Well, minus x and plus 2. So we're subtracting this. And x minus x, 0. 5 minus 2, that's 3. So our remainder is 3. So what does that mean? What does that mean? That means that we will have the following. So x squared plus 3x plus 5, and this is called remainder. So something we cannot divide anymore. So x squared plus 3x plus 5 over x plus 2 is actually going to be, so we're going to have our expression by itself, x plus 1, and then we're going to have plus our remainder, 3 divided by x plus 2. Okay, so we were able to divide that fraction, but what happened was that it's not divisible without a remainder, so we left over with the remainder, which is 3 plus x over 3 over x plus 2. Okay, so essentially, the way we divide it is called, the long division is essentially a division algorithm, right? It's a very famous division algorithm in algebra. So that division algorithm, essentially we can say that if f of x and d of x are polynomials such that d of x is not 0, and the degree of d of x is less than or equal to the degree of f of x, then there exists a unique polynomials q of x and r of x such that we have a f of x to be dividend, and divisor is d of x, quotient is q of x, and remainder is r of x, where r of x is equal to 0, or degree of r of x is less than the degree of d of x. If the remainder r of x is 0, then d of x divides evenly into f of x, right? So in the first example, we had a remainder to be equal to 0. In this example, we do have a remainder, right? This is our, essentially, the remainder of 3 over x plus 2, right? That's our remainder. And sometimes, in a lot of problems, we will not have a remainder to be equal to 0. But that's a good practice. Now, that was the long division. Now let's go ahead and actually talk about the synthetic division. Right, synthetic division is essentially very similar to what a long division is, just only in coefficient matters. So here we have to be careful with what kind of coefficients we have. And let's do a synthetic division for a cubic polynomial. Right, and here we have a synthetic division for a cubic polynomial. So let's say we're trying to divide ax cubed plus bx squared plus cx plus d by x minus k. So we're going to be using this pattern below. So we write down the coefficients in order of powers, right? So we have order of powers here. We have x cubed, x squared, x1, and x0, right? That's what we have. And then, well, we're going to take down the coefficient, and then we say, okay, well, a times coefficient k, we're going to have, okay, we're going to add them. So vertical pattern, add the terms in column, right? So we're going to add them. So we're going to get ka plus b. Diagonal pattern, we're going to be multiplying. So we're going to be going it like that. So we're going to be going to do it in this pattern. So let's actually try to look at an example, right? It's going to be easier to understand it with example. So let me go ahead and erase this. So let's go ahead and do an example. right? So I'm gonna have example 3 here, and that would be, well, we want to have, well, not only cubic polynomial, but let's do just a random polynomial here. So we're gonna do x to the 4 minus 10x squared minus 2x plus 4, right, divided by x plus 3. Right, so it's similar. So what's our coefficient here? It's our coefficient, so our k is -3, right? Because we have to have this format here. So k is equal to -3. So let's write down, we're going to have -3. Then our first coefficient is 1. Our cubic coefficient is 0. That's important here, right? Then our square coefficient is -10. First power coefficient is -2. And then 0 power, it's 4. Okay. Okay. So let's do that. So we have 1 and 1 here. So we have -3 times 1. That becomes -3. Now we add them. Right, now we add them. So 0 plus -3, that is -3. Okay. Okay. Perfect. Now we have -3 times -3. That's 9. So we're going to go ahead and add them again, right? So -10 plus 9, that's going to be -1. Okay, then -1 times -3, that's going to be 3. So we're going to go ahead and add them once again. So -2 plus 3, that's going to be 1. 1 times -3, that is -3. Right, and now we are adding them once again. So 4 plus -3, that's just 1. So this is our remainder, right? Remainder. We did divide it with remainder, but what would be actually the equation here? So we have decreased the power. So we will have x cubed minus 3x squared minus x plus 1, and our remainder right here. So our equation actually, right, becomes, so x to the 4 minus 10x squared minus 2x plus 4 is divided by x plus 3. So it has become x cubed minus 3x squared minus x plus 1 plus our remainder, and the remainder is 1 over x plus 3. Right, so synthetic division is slightly faster than long division, but it depends on the problem of what are we trying to do. Right, sometimes it might be easier to do the long division, right, because synthetic division works well with the linear, if the denominator is linear coefficients, right, and it's just easier for us to solve, right? It's simpler for us to solve and faster. But if we need to get the remainders faster, we can use the synthetic division, especially for dividing it by a linear x minus k polynomial. So essentially, here we have a remainder theorem, right? So the remainder theorem, that is a part of the division algorithm, and in general, because synthetic division is a division algorithm, so we can say that, well, the remainder theorem, if a polynomial f of x is divided by x minus k, then the remainder is r equal to f of k. Right, and we already kind of seen it, right? It's a remainder with some sort of coefficient, right? We're going to have either coefficient. Sometimes we have coefficients, sometimes we might have an entire polynomial there that is not going to be divided. But most of the time, for real parts, for real polynomials, we're going to have coefficients. So definitely double check the computations when you are doing the long division or synthetic division. Okay, but now we also leads us to, so the remainder theorem, right? If the remainder is 0, right? If the remainder is 0, we can prove, right? We can prove that the polynomial f of x has a factor of x minus k if and only if, right, f of k is equal to 0, right? Right, so when the remainder is 0, then we know that x minus k is a factor of the f of x, right? X minus k is a factor of f of x. So, all right, but we're not going to be proving it, but that's essentially, gave us an idea from the remainder theorem that if we have a remainder and the remainder is 0, then we know almost for sure that the polynomial f of x has a factor of x as x minus k. So we also had last time we talked about the upper bound and lower bound. So now, since we know a little bit about synthetic division, long division, we learned it, and we practiced some problems. So we can take a look again at the upper and lower bound rules, which we did last time. So if the polynomial was real coefficients and positive leading coefficient, and we're dividing it by x minus c using the synthetic division, right? If c is greater than 0 and each number in the last row is either positive or 0, then c is the upper bound. with the real zeros of f. It's going to be the highest upper bound, or the highest zero. And then if it's less than 0, right, in the last row are alternately positive and negative zeros, entry counts as positive or negative, then C is the lower bound for all of the real zeros, right? So we have the following. We have two. Let's see. So we are working with the real zeros and the real zeros of the polynomial. So let's take a look at an example. So so f of x is equal to 6x cubed minus 4x squared plus 3x minus 2. And here we'll have, remember, our rational zeros are those zeros which are factors of the leading term and the ending term. So here, what are the factors? So factors of -2 divided by factors of the leading coefficient, which is 6. So what are the factors of -2? It's going to be plus or minus 1, plus or minus 2. How about 6? It's going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Okay, so that is a lot, right? So what can we have? We can have plus or minus 1, plus or minus 1/2, plus or minus 1/3, plus or minus 1/6, plus or minus 2/3, and plus or minus 2. Okay, so we know that the original polynomial f of x, right, by Descartes' rule, has 3 variations in signs, right? So here, if we find f of -x, that's going to be -6x cubed minus 4x squared minus 3x minus 2, right? This polynomial has no variation in signs, so by the Descartes rule, there are 3 positive real zeros, or 1 positive real zero and no negative real zeros. So if we use sympathetic division, right, and let's test it for the first term here. So -1. So let's say that we're going to divide 6x cubed minus 4x squared plus 3x minus 2, right? If we divide it by x minus 1, so we're going to have by coefficients we have 1, right? And we're going to have here 6 minus 4, 3, -2, right? So we're going to have 6 times 1, that's 6. We're going to add it, that's going to become 2. 2 times 1, that's 2. We're going to add it, that's going to become 5. And then 5 times 1, that's 5. 5 minus 2, that's 3, right? So x equal to 1 is not a 0. Is not a 0. So, but the last row, so the last row has positive entries. However, we know that the x1 is an upper bound for the real zeros. So we have to be somewhere less than that, right? We got to be less than 1. So well, most of them are less than 1, but let's take the closest one out of all of them to 1. So we know that 2 cannot be the 1. So we can determine, let's try to say, well, x minus 2/3 is equal to 0. So if we try that, we actually will be able to. So we have to be less than 1. So it's not a 0, but x, I guess I will say x0 must be less than 1, somewhere less than 1, right? So we can also find a lower one, but we're not going to do that here. So the next less number, which is less than 1, is going to be the 2/3, and happily, we will find out that that 2/3 is actually the factor. So we're going to have x minus 2/3 times, so if we simplify, do synthetic division, we're going to get 6x squared plus 3. Right, so that is a factor. Right, so we have one real root, and this root is not real, it's going to be complex. Okay, so perfect. Now, let's talk about so we were talking about some polynomials, right? And we already dealt with some fractions. We haven't yet talked about the properties of these fractions because we were just doing the long division and synthetic division. But when we talk about the rational function, right? So a rational function is essentially, we can think of it the following way. So rational function, we will have f of x to be equal to some function n of x divided by d of x. Okay, right, and we have to make sure that, of course, d of x is not equal to 0. Right, we have to make sure that either domain is restricted or the function in general is not 0. So when we are talking about a rational function, right, we will define an asymptote. Right, so an asymptote of the graphs, and we will give some examples of those. So one of the example of the asymptote is when we are talking about the function 1 over x. Right, so one of the example would be here. We have 1 over x to be our function. So this is a 1 over x. We have a horizontal asymptote of y equal to 0, and we have a vertical asymptote of x equal to 0, right? Because the function is not present when y is equal to 0 or x is equal to 0, right? It does not exist. So some of the properties and definitions of vertical and horizontal asymptotes that we need to know. And here it is. So if the line x equal to a is a vertical asymptote of the graph, then we have that f of x approaches infinity, or f of x is approaching negative infinity as x is approaches a, either from the right or from the left. And the line y equal to b is horizontal asymptote of the graph of f when f of x approaches b as x approaches infinity or negative infinity. Right? So here we will have a few more examples. Right? Let's take a look at a few more examples of the graphs. So we might have something like this. Right? Let's move it a little bit here. And here it's going to be an examples. So for the first example, we do have function f of x, 2x plus 1 over x plus 1. So here we have a horizontal asymptote of y equal to 2. So here is also an important thing to remember, which we will talk about the powers, right? So the powers will tell us, the powers of the polynomials will tell us when we have some of the horizontal asymptotes. So vertical asymptotes are usually coming from the denominator, right? So we know that x must not be equal to -1, so that's going to be our vertical asymptote. Then similar for this problem, so we know since x squared plus 1 is positive and it does not cross the x-axis because it does not have real zeros, then we only have a horizontal asymptote of y equal to 0. And then this example, 2 over x minus 1 squared, we have a vertical asymptote at x equal to 1, and then once again we have a horizontal asymptote at y equal to 0. Okay, but how does the asymptotes actually relate to the powers and to the functions itself here? So here are going to be the vertical and horizontal asymptotes rules. So let f be the rational function, right? F of x, this is going to be the f of x, right? So we have two different powers, right? N and m. So the graph of f has vertical asymptotes at the zeros of d of x. So d of x is the bottom, is our bottom polynomial, right? D of x is equal to bm x to the m plus bm minus 1 x to the m minus 1 plus dot 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 plus b sub 0, right? So the zeros of it will give us vertical asymptotes. So the graph of f has at most one horizontal asymptote determined by the comparing degrees n and d. So we have to compare the degrees. So in here, how would we do that? So when n is equal to m, the graph of function f has the line, the first leading coefficient, a sub n divided by b sub n, right? So here in the previous example, that's how we found it. So we know we have the leading coefficient has power 1. So we're taking 2 over 1. So we have both have 1. So 2 over 1, that's going to be 2, right? That's if, when you compare, so that's when we have the, they're equal. When n is less than m, so the m is dominating, the graph of f has a line y of 0, right? And we have it right here. So in the numerator, we have a 0, and the denominator, we have a 2. So 2 is greater than 0, so we have y asymptote. Similar case here. So for equal powers, we have simple a sub n over b sub n. And a sub n is the leading coefficient, b sub n is the leading coefficient for the denominator. And then if n is greater than m, the graph of f has no horizontal asymptotes. So the numerator is essentially dominating over the denominator. All right, perfect. So those rules you can apply to functions and to rational functions in order to find the asymptotes. And the last kind of asymptotes that I mentioned are called slant asymptotes. So if we have, right, if we have a fraction, right? X to the power of n over, so x to the power of m, essentially, right? We have a polynomials. And if we know that n is exactly one more than the degree of the denominator, so n plus 1 is greater than m, and if n is equal to m, right, so essentially that's the case, right? If n plus 1 is greater by 1 unit, then we're going to have the slant asymptotes, or also we can call them oblique, right? So let's take a look at an example. So if f of x is equal to x squared minus x divided by x plus 1, right? If we do the synthetic division, we're going to end up with x minus 2 plus 2 over x plus 1, right? And how does this graph going to look like? Well, let's take a look at it. So the slant, or essentially oblique, asymptote for this graph is going to look like this. Here it is. So we have a vertical asymptote because x cannot be equal to -1, but this is our function f of x, and once we did the synthetic division, our slant asymptote is actually x minus 2, right? This is our slant asymptote here. All right, perfect. So that would be it for today's lesson, and I will see you guys in the next lesson.